All right, this is the solution for E, a recurring problem. The problem is you are given a list, well, in theory, you have created a list of positive linear recurrence relations. And a positive linear recurrence relation is something, for instance, the Fibonacci series, where we pick some starting coefficients, 1 and 1 in this case of the Fibonacci sequence, and some coefficients to generate the rest of the sequence, 1 and 1 in the Fibonacci case. And then you have, for instance, A3 is equal to 1 times the sequence element 2 before, plus 1 times the sequence element 1 before, and then you just continue this forever. So this is how recurrence relations in general work. And we have stated that all of these are positive integers. Now, we've taken the entire set of all of these recurrence relations and we've put an ordering on them. Now, the problem is, given a number in the ordering, what is the recurrence relation that we are referring to? Now, this is a very difficult math problem, and it can be solved in various ways. But the main, the crux of how you solve this is you ask these questions of, for instance, how many continuations start with 8, right? So you might ask, how many ways can we pick our A's and our C's such that the first element that is generated after the A's is 8? And as it turns out, for just one number, for 8 in this case, it's actually not too bad to solve this. It turns out to be the number of ways of picking A's and C's such that 8 is this product of the A's and the C's. And you can solve this with a dynamic programming approach. This is not too hard. So this will tell you fairly simply what the first number that you're looking for is. But unfortunately, you need to go on, and then it gets more complicated, a lot more complicated. So now you have to ask a question, for instance, how many continuations start with X, Y, Z? And so the problem is now when you pick an A and C in your dynamic programming approach, you're subtracting off A times C from X, but you're also subtracting off X times C and Y times C from Y and Z. And so basically earlier elements of the sequence start to affect the later elements of the sequence. And we can generalize. So we can still use dynamic programming, but it's a complicated dynamic programming on vectors. And so this is our more general version of dynamic programming that we use here. So for instance, if our most recent elements here are M and N, and the sequence we want to end up with is X, Y, and Z, then we run a dynamic programming which picks A and C, just like above, it picks A and C, and then it recurses to, for that choice, it recurses to this subproblem, which is you subtracted A times C from X, and you've subtracted the previous two elements times C from Y and Z. And so this shows you how to solve it for a vector of length 3, but it generalizes to vectors of smaller or larger size. So this is how you answer this general question. And then, of course, once you've been able to answer this general question, you can just keep on asking how many continuations start with blah, and so on and so forth. You keep on increasing X and Y and Z until finally you hit the right number, and then you can print out the sequence. Now, there's only one problem. This dynamic programming on its own does not run in time. This is too slow. And part of the reason is this space is very complicated. You have a lot of cases where you ask X, Y, Z, and there is no answer. Because the thing is, this DP eventually has to hit 0, 0, 0 for there to be an answer. And you might take a lot of choices that don't end up hitting 0, 0, 0, and you've wasted your time. So you have to figure out how to optimize this, and this is what really makes the problem difficult. Most teams could probably get this far, but the optimizations are really difficult. And so one way of optimizing, I'll say that there are several different ways that judges have come up with to possibly optimize to get into the region that we ask for, which is about 1 billion recurrence relations. So one way is you might pre-compute some of these answers and then put them into your code directly, and I'm not going to cover that. Another way is you might want to binary search, so you might want to ask, instead of X, Y, Z, you might want to ask x, y less than or equal to z. And then you can pick various z's in binary search. And because later elements in the sequence can be large, this can save you a lot of time. But the most effective way, I believe, is when you run this DP, you don't just return how many elements match x, y, how many elements or how many coefficients, choices of coefficients lead from x, y, z down to 0, 0, 0. You don't just return that. You also return a list of all the possible next elements of the sequence. So you might say that, for instance, x, y, z, w, for some w, has 136 possibilities. And then you might say that x, y, z, u, for some other possibility, might have 5. And sometimes you'll say that it has 0, in which case you won't even bother trying that in a later iteration of your DP. You'll just know ahead of time that, no, there are no answers. And because the space has very interesting structure, you will actually save a lot of time by skipping sequences that do not have a solution. And one example is, for instance, if you ask what can follow 9 and 17? Well, you actually have lots of answers to 33. And you've got not so many to like 31 or 32 and 34 and 35. And then you've got lots of answers to 41, and then there's a gap where there aren't very many answers, and so on and so forth. So what you have to do is you have to identify, you have to use this map to target your search into only the sequences that are eventually going to be able to hit 0, 0, 0 as you desire. And then if you do that properly, and you are an absolute best in the world team, then you can probably get an answer and solve E, a recurring problem. Thank you.